show.
Very good. Good turnout today. I got a full screen load. That's a good day. And most of you are probably aware that I'm Bill Ragsdale, originally the founding president of the Fourth Interest Group and have shepherded for about 4 years. And then Glenn Tenney took over, and then other people took over. And so the completely rewarding result is that this group has met continuously now since about 1978. So with that, we will go to a presentation.
If you're not muted and you're not Bill, now's the time to hit the mute button.
Green. All right. Very good. Welcome. As I said, Bill Ragsdale here, and today we're going to have a delving into some of the aspects of float numbers. It's a project that I kind of started on a long time ago, 15, 20 years ago, something like that, and did research then, and it sat on a shelf, and there was no particular need, and now the need has come up recently for some using some very specialized floats on from a historical basis. So the starting point is that in the financial community, there was a company called CompuTrack back in the 80s that came out with a financial analysis, a stock market analysis program, CompuTrack. And they were the pioneer in all of this in the personal computer area. There had been some work in the commercial areas. So they set a standard using floating point at that time, which was from, I think Microsoft had it in QBasic or QuickBasic at that time. And it has carried through, as we will see, to the current day. So beware of what you start with a design, because from the mid or early 1970s, this format is still in use very, very heavily. So on the chart here, we see what how a securities price line would appear on the screen, where we get the date, the high, for the, in this case, for the week, high, low, close, and volume. So I wish to do analysis on a data, an extensive database using this format. It's a 32-bit structure. It has an 8-bit exponent, a 1-bit sign, and a 23-bit significand. And it has a surprisingly limited range of, by memory, I forget what 20, what actually, it has a 24-bit representation. So it's something I think in the under 20 million plus or minus for full resolution. The numeric range goes into, of course, into the billions, but for maintaining full precision, I think it's only about 16 million something. So back in this time, we'll see M popping up here, which in these days is called the significand. It's the number part, the actual expression of the value. In those days, in the 80s, 70s, it was called mantissa, which is more of a logarithm word. So I'll continue calling it significand, even though some of the diagrams are going to have M's on them. This format has the binary value left justified, and this is the universal trick, I think, that's all done in floating point. And that is, since it's left justified, there will always be a 1 in the leftmost position. So since it's always there, it can be omitted. So there is an implicit bit in our discussion here in the position of bit 23. So that bit is omitted and implied when the number is normalized. There are representations in which it is not normalized. In that case, all bits are present, but we're only going to talk about the normalized case. And another little trick is that 0 has no place to have an implied 1 bit. There is no way to left justify a 0. There is no bits there. And therefore, it's a special case that the number 0 is always defined as a fully 0 value. All 32 bits are 0. 0 exponent, 0 sign, 0 significand. 0 is 0. To do troubleshooting and development, I have firstly developed a word I just call B dot, which is a binary printout. And you can see the headers are in there and then conversions. And green at the bottom is the result we're going to see. So we give it a 32-bit number, and it will spread it out into bytes and number the bytes as they go along from right to left. And that little magical bit 23 has an X on it because that is where the implicit bit would be, and it's also where the sign is located. So it's a navigation point that in debugging we look at all the time. To the left of the X is the exponent. So the general representation of a floating point number, the components that are used is there's a representation for the sign, there's a binary representation for the significand, and then there is an exponent, which is a power of 2. And they apply an offset to this, which in simplicity, I would just omit the offset. But to avoid having exponent with negative values, the actual exponent of the significand is offset. In this case, I believe it's by the number 127. So this is what the floating point number would look like, starting from the right to the left. Bit 0 all the way up to bit 22 is the significand represented by M's. Bit 23 is the sign, and then the top 8 bits is the exponent. And we put a little green note with a little up arrow there saying that if it was there, the hidden bit would be located at that position of the caret. Oh, here's an example that we will look at a number. Let's look at the number -7. And in a moment, we'll see the code that does this conversion. But this is to convert a single number, a 32-bit stacked number, to this MS format. And there's a little bit of a double entendre here because MS can be Metastock, or a Microsoft format. It also can be Metastock because the dominant company today using this format is called Metastock. They're out of Salt Lake City, and they are very, very widely used. So it's either a Metastock or Microsoft. And the B dot applies that conversion we saw a moment ago. So here's what the numbers -7 would look like displayed. We see the exponent on the left, the sign bit under the X, and then the significand 23 bits long, and of course that implicit bit missing. And a way to verify that this is the number 7 is 7, of course, in binary is 111. If we knock off the leading bit due to its hidden nature, the remaining 2 bits of the 7 is in the circle 11. So there's a quick peek at a floating as a Metastock floating point number, and the exponent in this case is 83. Read the hex there, and it says exponent is 83. So this is the word that does the conversion. We'll look at that in stages. Remember, for a number 0, the input and output is always 0. So the very first line, dupe 0 equal if exit then, will return to 0. And execution is done. And if it continues, then the first step is to strip the sign off. And so the dupe 0 less than if, go to absolute. The 0 less than says if we have a negative number, we convert to absolute, and then put out the bit pattern which represents a sign bit set. That 1 8 in there is in the bit 23 position where the sign is located. Otherwise, the else part is a 0, meaning a positive number. Now we begin some intense bit manipulation. The hex value 0x98 is a hexadecimal prototype of the exponent. That is an exponent for unity. If our input is 1, then that is the exponent for the number 1. And then the swap brings to the top of the stack the input number that we're examining. Now we set up a do loop. It's over 24 bits from 0 to 23. As we know, that'll execute 24 times. And we examine the do dupe 0x008 tests the most significant bit. And if it is set, we leave it that first loop through. If not, the else part does a left shift, which multiplies the significand by 2, and then the swap minus 0x01 subtracts 1 from the exponent. So we multiply the significand by 2, and we divide the exponent by 2. And that continues in a loop until we have finally reach a leftmost justified value. And we have shifted that leftmost value into that little X position. And in a moment, it's going to be cleared. So at this point, the 0x007 with all the Fs, that masks away the hidden bits. So we've shifted clear to that last 23-bit position. Tested it, stopped our adjustments, and then mask it away. The OR, R from OR, ORs together the 3 components. It ORs together the sign, the exponent, and the significand. So there is our number complete. And we'll look at it again. This is what we saw before. So that calculations produce the exponent in the leftmost 8-bit positions, the sign, and then our significand. So that converts a stack number. We can key in an integer and convert it into this particular format. It's still on the data stack. Now, this is a conversion. So if we want to go from the internal floating point format of, in this case, Win32 it uses the IEEE 64-bit floating point format. So in this case, the floating point number is on the floating point stack, and we develop the Microsoft float value on the data stack. It's very intensive on bit manipulation, as we assume. Notice at the beginning, we do the fdupe f0 equals. In the case we have a 0, we drop the floating point number and exit with a 0. And again, for 0, 0 in, 0 out. Otherwise, the green FS to DS says floating point stack to data stack. That transfers a binary image of the floating point number that's on the floating point stack unmodified to the data stack. And we now have a double number, 64-bit value on the data stack. The following code then does a lot of shifting and masking, and it puts the and we'll see this action going on in a moment in real time. There's a lot of manipulation going in there, and writing it and debugging it, as you can imagine, is an intense effort. And so I put in a diagnostic test for every line of code, so I could essentially single step through and look at the execution at each point. And I would start with a simple number like -7 and run through and watch how it processed, because it is fairly easy to follow. So here's what the debug process looks like. We start out with that IEEE number, which we're going to convert to metastock. And in fact, that first case, it's a 0. It's this is the lower 32 bits. The upper 32 bits is at the bottom, the raw high 32 bits. That's the this is the IEEE form in the high 32 bits. The low 32 bits, as we see, are 0. And there again is our friendly little 1, which is the um, low 2 significant bits of the number 7. We won't go through all the processing here, but the exponent is developed, it's shifted, its offset is adjusted. On the top left, the exponent is placed in the proper position. Down at the bottom, sign bit is in bit 31 position. It gets positioned over to where that X bit is. Actually, no, it isn't. It's positioned, yeah, it's oh, that's correct. It's positioned to that X bit, which is where the sign is supposed to end up. And then the significand is adjusted. And finally, now we have our output that we learned to know and love, which has the exponent is hex 83. The under the X is the a 1, which represents a negative number, and then the 1 in the red circle are the 2 lowest significant bits. So there is our conversion from IEEE to the MS format. This is the conversion in the opposite direction. Hold a second. All my ham radio buddies are talking at me. In this case, we're doing the Microsoft to IEEE. In this case, this is done on a floating point stack. In the prior case, the conversions are all done on the data stack. In this case, a lot of the conversions involve exponentiation, and they're done on the floating point stack. So again, we start with a dupe 0 equal if a single to float exit. What that does, the S to F takes the single number and converts it properly to the IEEE number. Essentially, a 32-bit value is converted to a 64-bit value, all zeros. Then at the line down or so, we see a fairly complicated line to restore the hidden bit. There's a right shift, a 23-bit right shift. And notice this is done in floating point. So you have a lot of fun learning how to think in fourth binary and execute as floating point numbers. But that division there will do on the floating point stack does a right shift. Then the following numbers we come down are removes the exponent, and then the 2e single to float f star star raises the 2 to the exponent of raise it to the value of our exponent, and then we multiply that on the significand, so that scales the floating value. And finally, at the bottom, we bring the sign back, and if that sign is set, we then do a floating point negate. So magically, all this ends up in the floating point stack. Here's some examples of the use. At the start here, we have 0e, which is a floating point 0. We convert that IEEE to MS, then we convert MS IEEE, F dot prints it, and we see 0. So we've done a two-way conversion, and both conversions agree. Just for grins, we try a -0, and it's accepted properly. And then the S to MS, which is from the data stack to the floating point stack, again, put a 0 in, convert it to Microsoft, take the Microsoft IEEE, print it, and again, we get a 0. And finally, now we are just trying some simple numbers. From the keyboard, we can type in the -1, 2, 3, 4, 5, 6, 7, convert that single number to Microsoft IEEE, print it, and sure enough, we get our proper number, and a decimal number tested does the same way. So everything is good. The input to the Microsoft format from the keyboard is 32 bits, or up to 32 bits, an integer, but there's no way to express a decimal point. And I didn't want to go into a lot of parsing, having to go pick apart numbers and do decimal conversions. So I took a simple way out, which is to put on the stack two values. N1 is our input number, and N2 is the desired decimal place. And so it does the conversion, and our output N3 is the Microsoft format, but it has a decimal conversion. And this is done on the floating point stack because it's the easiest place to do it. And so the 10E S to F star star raises the exponent, converts it to a floating point number, and then we multiply our input by that number, which offsets it either plus or minus, and we'll see the example here. If we input 1, 2, 3, 4, 5, 6, and then say we want to shift to 3 decimal places, the S.D to MS, and then display it, we see that sure enough, we have our 1, 2, 3, 4, 5, 6 followed by 3 zeros. If the exponent is specified as negative, we go through the whole process, and now the decimal point has been shifted 3 points to the left. So here's a very convenient way for testing and for applications in interfacing the fourth keyboard entries into our floating point format. And so as I'm doing my analysis later on, I am able to convert two ways to and from the databases I'm examining into 4 stack values. So to wrap it all up, you see some of these conversions are done in the data stack, which is when it's more convenient, primarily with shifting and masking. And then the others are done on the floating point stack when we're doing scaling and exponentiation. So your thinking has to be flexible, and you have to be facile in both worlds of integer and floating point. When I started doing this back in 2005, 6, 7, 8, somewhere around in there, I couldn't find the floating point format expressed anywhere. And due to a book search, I was able to find an obscure QBasic book written by a Russian gentleman on QBasic or Quick Basic, paperback book, but it had the format in it. Now you can do a Google search and it'll pop right up. So this format that we're looking at came about, as I said, in the early mid 70s, 80s. I guess it was about the time the PC came along. That was the target that they developed the software on. But because of this early mover advantage, everybody that came along afterwards copied the CompuTrack format. The data suppliers had downloader programs that would download into that format, and so everybody wrote on the coattails of CompuTrack for that first move. And since then, there were about 6 competitors that came along in the following 5 or 6 years, all using that format, and it continues to this day. There are some other formats used, but this one, I'd say, is quite popular. And I worked out a number of diagnostic and testing and manipulation routines to use that format. But if I'm doing real math on it, I will not be using that format. I'll be going basically into fourth integer and floating point. So that is my presentation. Do we have any questions or comments?
Do spreadsheets use BCD? Because VisiCalc used like BCD. I don't know if they've changed the floating point from modern spreadsheets.
Paul, you've got a big echo in your audio.
I know.
I assume spreadsheets are pure binary. I don't think they would go to the complexity of BCD. Remember, our faithful old 6502 had a mode for BCD arithmetic. So you could put in byte-oriented characters, 4 bits per decimal number, and you could do addition, and it would do the carry between bytes. But the 6502 is the only CPU I'm aware of that does BCD arithmetic.
Well, Intel had a conversion between BCD and decimal. I don't know if the tradition of VisiCalc carried forward to the modern spreadsheets.
Any other questions? Well, like I say, I compliment you. We had a good turnout today, even more people. So I'll turn it back now to Kevin. Thank you for your rapt attention.
Bill, the this propagated, but did it find its way into the world just because everything was being written in this QBasic dialect, or did some people look at it and say, "Oh, that's a good format. I'm going to do it that way," even though QBasic was available and they didn't use it?
I don't know what the original CompuTrack system was written in. I wouldn't be surprised with what it was QBasic. It had well-developed graphics because a lot of the stock market analysis is done for technical analysis by graphics, drawing lines, curves, exponentiation, and so on. So the key factor was that you downloaded your data every day from sources associated with the national stock markets. In other words, the the stock markets would report in real time securities prices. They go to data providers who inventory and sort the data. And then typically once a day, your software would phone into a central database and download whatever securities information you want. So that process uh, was distant and was rigid and would be hard to create any alternatives. So whatever it was ruled. So once you got the download, then the file format at that point used this QBasic floating point. It's the CompuTrack format. In the database, there's a header on it for each security. There's a header, and it talks about uh, they had quite a number of scale factors. They had 5, 6, and 7 uh, field format and so on. But once you mastered that CompuTrack format, everybody else said, well, I'm going to follow it. I'm not going to go do my own because that's the format in which the data is downloaded. And so the 6 or so competitors that came along all followed that format. And most of those competitors have now gone away, but replacements have come along over the years. The dominant company is Metastock out of Salt Lake City. At one point, it was owned by Dow Jones, who runs Wall Street Journal and so on. But Reuters now owns it. Reuters is an international information provider, but they still keep that same old format going.
Those of you who have a camera want to please turn it on now. In a couple of minutes, we're going to do a screenshot just so that we have a
Yeah. I wanted to mention
memory of these.
for Bill, just a second, I didn't get a chance to speak there. The 4004 and the 4040 both have decimal arithmetic capable.
Yeah, they were developed as for a desk calculator. So,
Yes.
well, they should.
Yeah.
Well, they should.
Yeah.
I used to sit at Mike Quinn's store in Oakland. I used to go in the parking lot and argue with George Morrow on the architecture benefits between 4040 and 8008. So that was our trip down memory lane with the late George Morrow.
Definitely the APL world, the original purpose, there was a early company, scientific time sharing, but the use ended up being financial markets and so forth. And one of the amazing things to me was when the PC came along with its 8088 or 8088, yeah, 8-bit bus. A guy named Phelps Gates actually managed to get APL running on it. But and again, the market has always been financial. Yeah, never worried about. I mean, yeah, solved the floating point. Just sort of essentially as being part of it. Going back way back, I don't know, way back. Before that, everybody was on 68,000s, which are a far more capable chip.
Bruce, did you have something you wanted to say?
Yeah, I wanted to ask Bill if he considered looking at hardware accelerators, the 9511 going back, showing my age, which has hence been folded into the processors of Intel.
I'm a user, not a creator. I take the box the way it comes from Costco, and I just put my code on the box, and that's it.
Okay, well, the processor's there. That's why I was asking. It's part of the instruction set.
I no,
He's saying that whatever
I'm
floating
likewise
point.
too. These days, I'm a fourth user, not a fourth creator. I'm using Andrew McEwen, Win32 fourth, and it solves all my needs that I have. And if it doesn't solve it, I don't need it.
Okay,
I think
thank
the
you.
floating point is that fourth is the fourth that is the floating point that uses the IEEE format and the coprocessor. So
Yeah, it certainly does use the coprocessor. So, and Win32 fourth floating point math is just about the same speed as integer arithmetic. I
yeah.
believe integer arithmetic goes through the floating point processor also.
I don't think that was Bob Smith, but the floating point definitely was descended from Bob's work. All right. There are ne'er-do-wells among you like Ken and Yang who haven't turned on their cameras, but what could I say? Thank you. Okay, are we ready for the screenshot, Brad?
Yes, we are.
All right, everybody, hold still. It's like the olden days where the shutter release was pressed and the camera exposure was completed over a period of perhaps 20 seconds or maybe more.
I have the screenshot. It actually looks pretty good this time. Let's see if
I'm pleased to hear it. Oh, I was hoping Joseph would just have the nice picture, the resume picture with the tie. Hi, Joseph. It's good to see you, even in
I'm
Corpus.
okay.
I'm just,
Yeah, it looks a
I'm
little bit
just,
more professional than my SV Fig getup.
I don't think we need to look professional at this time.